Good evening and welcome back. Tonight, we begin a long, slow ascent into the silent, eternal architecture of the cosmos. The story of the history of ancient astronomy and celestial myths' gentle sleep tale. We will trace the quiet gaze of our ancestors, the soft patterns they perceived in the dark, and the serene dreamlike stories they wove around the distant stars. I invite you to share where you're listening from. Let the atmosphere of your own quiet room tone settle softly around us. Settle in now. Find warmth and soften your breath. Allow your awareness to drift upward, releasing the gravity of the day. Remember, there is nothing to solve, nothing to resist. All the plans and tasks can wait until the morning light. Let my voice be your soft anchor tonight, guiding you into a deep, restful calm. We are drifting back through time to the first campfires and the first quiet nights towards the ancient rivers that reflected the silent celestial parade under the deep expanse of the quiet night. Nothing in tonight's story will disturb your peace. Let the gentle greetings settle over you. Now allow yourself a long, slow breath in and out, releasing any lingering tightness. Imagine the air around you is turning soft like mist, past moonlight, settling over a desert observatory. We are entering an ancient myth-like cadence, where the vastness of the sky has been filtered and softened into serene visuals. Time moves slowly here, measured only by the steady, slow tides of the turning constellations. Our journey will follow the faint, winding arcs of the planets, ensuring no tension interrupts your drift. If these gentle journeys help you rest, you may leave a soft like or subscribe, only if it feels comforting and natural for your night. Chapter 1. Origins. The first gaze and the quiet patterns. We begin our long narrative at the ultimate origin and the simple, fundamental act of looking up. This is the ancient background tracing the very first moments, long before telescopes or written records, when humanity began to perceive order in the overwhelming expanse of the distant night. Imagine the earliest observer, perhaps resting beside a low ember of a campfire, captivated by the unchanging canopy of stars. The origin of astronomy is rooted in this fundamental human experience. The recognition that while the terrestrial world is fleeting and full of change, the celestial world is perpetual, predictable, and serene. The first profound realization, the ancient root of all astronomy, was the quiet, absolute rhythm of the sky. Our ancestors observed the unhurried, systematic movement of the stars. They rise in the east, set in the west, and appear at the same location at the same time each season. This dependable cycle offered immense comfort and stability to early life, which was otherwise prone to stress and uncertainty. The stars became the first vast legacy of human memory. Before writing, the complex patterns of the constellations served as a mnemonic device, a celestial calendar visible to all. The groupings of stars were given names and stories not out of random imagination, but out of necessity. These myths became the gentle, universally shared language for tracking time, marking the start of harvests, and signaling the best seasons for migration or ceremony. The warm breath of the sky provided the earliest clock. The seasonal appearance of certain bright stars, like Sirius the dog star, rising just before the sun, was a crucial annual signal. In ancient Egypt, the heliacal rising of Sirius quietly marked the crucial, predictable start of the Nile's annual inundation or flood, which guaranteed life and sustenance. The sky was intimately, practically tied to the ancient rivers of the earth. The earliest celestial myths were less about grand, sharp conflicts and more about gentle metaphors for cosmic order. The sun and moon were seen as powerful, yet predictable deities, engaged in an eternal rhythmic pursuit across the sky, ensuring the continuous cycle of day and night. The predictability of their path, the ecliptic, became the quiet central reference line for all later complex astronomical calculations. This initial phase of origins was defined by patience and shared experience. Observation was passed down orally generation by generation, slowly accumulating the precise knowledge required to predict the movements of the sky. The sky was the ultimate distance softening filter for the chaos of the world, providing a sense of predictable, eternal harmony. Let the image of that first quiet gaze lifted to the unchanging stars above the ancient dust guide you deeper into rest. Chapter 2. Formation. The Babylonian scribes and the numbers. The quiet rhythm established by the first observers of the stars soon moved into a systematic phase of formation, driven by the organized methodical record-keeping of the Mesopotamian civilizations, particularly the Babylonians. This era transformed simple sky-gazing into true predictive astronomy. Imagine the land between the ancient rivers, the Tigris and Euphrates, where the clear, dry air allowed for meticulous observation under the distant night. The Babylonians, inheritors of the Sumerian tradition, were profoundly committed to recording and interpreting the sky. Their motivation was not purely intellectual curiosity, but the practical need for a stable calendar and the pervasive belief that celestial events held gentle metaphors for terrestrial happenings. The formation of Babylonian astronomy was built upon an extraordinary legacy of mathematics. The Mesopotamian scribes used a sexagesimal base 60 number system, which was perfectly suited for dividing circles 360 degrees and time 60 minutes or seconds. This methodical, tranquil system allowed them to perform precise calculations and record celestial positions with unprecedented accuracy, ensuring that this mathematical knowledge would flow through the soft wind of time to all subsequent civilizations. Their core work was the patient accumulation of data. Over centuries, the Babylonian astronomers, who were often priests, maintained vast, unhurried archives of cuneiform tablets. These tablets recorded the precise positions of the moon, the sun, and the 5 visible planets against the backdrop of the fixed stars. This was not fast-paced work. It was a quiet, relentless act of data collection, a commitment to perpetual observation. The Babylonians developed 2 key techniques that defined this formation. The zodiac. They mapped the path of the sun and planets, known as the ecliptic, and divided it into 12 predictable 30-degree sections, each associated with specific constellations. This provided a fixed, manageable reference system for tracking celestial movement. Predictive cycles. By meticulously comparing past records, they discovered recurring cycles in the movements of the sun and moon, such as the Saros cycle, which allows for the quiet, accurate prediction of eclipses. They recognized that while the visible world was unpredictable, the sky operated under a fixed, eternal mathematical law. The legacy of the Babylonian scribes was the transformation of simple observation into a robust mathematical science. They left behind not just myths, but a quiet, immense library of numerical data and calculated tables, a powerful testament to the idea that order could be found and quantified even in the vastness of the quiet night. Their methodical approach was the essential prerequisite for all later Greek and Hellenistic mathematical astronomy. Chapter 3. Early Journeys. The Egyptian Calendar and the Zodiac. The methodical record-keeping established by the Babylonians soon flowed into the Nile Valley, contributing to the distinct and profound early journeys of Egyptian astronomy. The Egyptians' focus was intensely practical, driven by the absolute necessity of predicting the slow river's behavior and the agricultural cycle. Imagine the banks of the Nile, where the most crucial event was the annual inundation flood. The Egyptians realized that the timing of this life-giving event was perfectly synchronized with the quiet heliacal rising of the bright star Sirius, which they called Sopdet. This annual coincidence was the fundamental origin of their entire calendar system. Their early journeys focused on observation over complex mathematics. By tracking the steady, unhurried appearance of Sirius just before the sun, they established the civil calendar, a practical tool comprised of 365 days, divided into 3 seasons: inundation, growth, and harvest. This calendar was remarkably accurate for administrative purposes, and became a lasting legacy of their patient terrestrial observation. The Egyptians also quietly ordered the distant night by dividing the sky's passage into decans. Imagine the night sky being systematically divided into 36 distinct segments. As the Earth turned, each of these 36 decans would rise and set in succession, allowing them to measure time during the night. This was a celestial clock, visible to all, acting as a serene practical tool for structuring their rituals and daily work. The gentle footsteps of these decans across the sky provided the basis for the eventual division of the night into hours. The later influence from the sophisticated Babylonian tradition, especially during the Hellenistic period, led to the adoption and adaptation of the zodiac. The Egyptians absorbed the Babylonian systematic division of the ecliptic, the sun's path, and integrated it into their own myths and temple architecture. This blending of the precise mathematical structure of Mesopotamia with the powerful enduring narratives of Egyptian religion was a softening filter for cultural exchange, ensuring that astronomical knowledge was preserved and beautifully synthesized. The purpose of Egyptian astronomy, unlike the later Greek quest for pure cosmic understanding, remained rooted in the maintenance of Mahat cosmic and earthly order. The stars and planets were seen as manifestations of the divine order, and the pharaoh's duty was to ensure that the earthly calendar and rituals perfectly aligned with the predictable, serene visuals of the heavenly cycles. This phase of early journeys solidified astronomy's role as the foundation of law, religion, and agriculture. The warm breath of their faith was intertwined with the cool logic of the calendar, establishing a powerful, quiet tradition of practical celestial knowledge. Chapter 4. Formation. The Greek cosmos and the perfect spheres. The precise mathematical records meticulously accumulated by the Babylonian scribes and the practical calendrical focus of the Egyptians were eventually carried across the seas by the soft wind of commerce and philosophy. This intellectual exchange initiated a new phase of formation. In the story of astronomy, the emergence of ancient Greek cosmology. Imagine the shift as a quiet move from the practical act of telling time to the contemplative art of understanding space. The Greek thinkers, resting on quiet stone benches under the Mediterranean drifting light, absorbed the data from the East, but asked a new profound question: why does the distant night move in this perfect way? This was the birth of cosmology, the search for the underlying reason, harmony, and architecture of the universe. The Greeks believed that the cosmos, a word that literally translates to beautiful order, must be governed by geometric and philosophical perfection. This contemplation provided immense psychological comfort, replacing unpredictable chaos with serene, eternal rules. The early thinkers, known as the pre-Socratics, began to propose gentle metaphors for the cosmos, moving away from purely mythical explanations. Thales of Miletus quietly contemplated the celestial sphere, and Anaximander imagined the Earth floating perfectly balanced in an infinite void. This was the moment when the physical structure of the universe began to be understood through reason rather than narrative. But it was Pythagoras and his followers who introduced the most soothing and enduring concept of this era: the harmony of the spheres. They believed that the sun, moon, and the 5 known planets were each mounted upon a series of nested, transparent, crystalline spheres. As these perfect spheres moved in their circular paths around the central Earth, they created a pure celestial music, a perfect and eternal harmony. This music was inaudible to human ears, accustomed to the noise and stress of the terrestrial world, but it was understood by the soul. This concept was not one of sharp conflict, but of complete rhythmic perfection, a universal, quiet lullaby. The formation of the universe was seen as the most beautiful mathematical and musical composition imaginable, providing a deep philosophical sense of security. The simple geometric forms, the circle and the sphere, became the fundamental legacy of Greek thought, representing eternal movement without beginning or end, and ultimate perfection. These geometric principles provided the tranquil framework upon which all subsequent Western astronomy would rest for nearly 2,000 years. The gentle footsteps of these early philosophers established a profound and peaceful tradition that the act of contemplation guided by reason could reveal the serene, hidden order of the distant night. Let the image of the transparent nested spheres turning silently in the cosmos, creating their perfect unheard music, guide you deeper into rest. Chapter 5. Early Journeys, Aristotle, the Earthly Center, and the Observatory. The serene geometric cosmos envisioned by the Pythagoreans and the philosophical quest for perfection established by Plato provided the intellectual foundation. The next crucial phase of early journeys was defined by Aristotle, 384–322 BCE, who solidified the dominant geocentric model of the universe through rigorous logic and observation. Aristotle, while deeply influenced by his teacher Plato, gently brought philosophy and astronomy back to the observable earthly realm. His key contribution was the systematic logical formation of the geocentric model, the idea that the Earth stands perfectly still at the absolute center of the universe. This concept provided profound psychological solace because it placed humanity at the stable central point of creation. Aristotle reasoned that the cosmos was divided into two distinct regions. The terrestrial earthly realm, everything below the moon characterized by change, imperfection, and linear motion up and down. The celestial realm, the moon, planets, and stars characterized by perfection, eternal motion, and the circular path. This division was a powerful softening filter, neatly separating the chaotic, changing world of human experience from the serene, unchanging perfection of the heavens. To explain the movement of the planets, which occasionally moved backward, a phenomenon called retrograde motion, Aristotle adapted and formalized the model of nested crystalline spheres proposed by earlier thinkers like Eudoxus. He posited a complex system of 55 concentric transparent spheres, each perfectly revolving, carrying the celestial bodies along their perfect circular paths around the central Earth. This immense complex mechanism required an unmoved mover, a divine force to quietly initiate the eternal, unhurried motion of the outermost sphere. The legacy of Aristotle's geocentric model was immense and long-lasting. It provided a coherent, logical, and aesthetically pleasing framework that perfectly integrated the astronomical observations of the East with the philosophical perfection sought by the Greeks. The concept of the celestial spheres moving with a predictable, quiet rhythm became the undisputed truth about the distant night for nearly 2,000 years. The warm breath of his influence spread through the Hellenistic world, where scholars like Theophrastus quietly established the tradition of systematic observation, laying the groundwork for later, more precise astronomical measurements. The gentle footsteps of his students leaving the Lyceum carried this logical, earth-centered view, cementing the belief that the cosmos was fundamentally rational and perfectly ordered. The search for geometric perfection had successfully created a beautiful, stable universe, perfectly tailored to human perception and reason. Chapter 6. Formation, Hipparchus, and the Seed of Accuracy. The elegant earth-centered cosmos of Aristotle provided the philosophical framework, but the subsequent phase of formation required the meticulous, systematic precision of mathematical observation. This transition was defined by Hipparchus of Nicaea, circa 190–120 BCE, the greatest ancient observer who gently introduced the necessary tools for accuracy into astronomical thought. Imagine Hipparchus at his observatory, perhaps on the island of Rhodes, working under the deep expanse of the distant night. His philosophy was rooted in detailed measurement, believing that the true order of the heavens could only be found by rigorously comparing current observations with the historical records accumulated by the Babylonian scribes and earlier Hellenistic thinkers. Hipparchus's contributions were profound, quiet acts of scientific formation. Trigonometry, Recognizing the limitations of simple geometry in calculating celestial distances and positions, Hipparchus pioneered the use of trigonometry. This mathematical tool, which we view as a gentle, precise mechanism for relating angles and sides of triangles, allowed for a massive leap in accuracy when mapping the celestial sphere. This was a necessary evolution, providing the warm breath of mathematical rigor to philosophical models. Star catalog driven by a perceived celestial change, perhaps observing a new star or nova. Hipparchus undertook the immense unhurried task of compiling the first comprehensive systematic star catalog in the West. He measured the position and brightness magnitude of around 850 stars. This catalog was a fundamental legacy, creating a fixed, reliable map against which the subtle changing movements of the planets could be measured. Precession of the equinoxes. Through meticulous comparison of his own star data with much older Babylonian and earlier Greek records, Hipparchus made his most famous discovery, the slow, continuous shift of the Earth's axis, known as the precession of the equinoxes. This shift is incredibly slow, requiring centuries of patient observation to detect. This discovery revealed that the celestial sphere, while seemingly eternal, was undergoing a gradual, predictable movement. This quiet recognition of long-term change was a profound softening filter on the static view of the cosmos. Epicycles, early concept, to reconcile the perfect circular motion required by Aristotelian philosophy with the stress of the observed irregular movements of the sun and moon. Hipparchus refined the use of epicycles, smaller circles upon which the planets moved, which in turn moved on the larger deferent circles. This geometric construct was a calm reinterpretation, providing a mathematical solution to save the philosophical perfection of the circle. Hipparchus therefore provided the essential formation layer between the philosophical structure of Aristotle and the complex practical modeling of Ptolemy. His emphasis on data mathematics and long-term observation ensured that the gentle footsteps of astronomical inquiry were now guided by precision. The quiet stone of his observatory foundations provided the necessary stability for all future advances. Chapter 7. Early Journeys. Ptolemy and the Almagest. The rigorous measurements and mathematical framework established by Hipparchus provided the stable platform for the next monumental phase of early journeys, the comprehensive systematization of the Greek geocentric model by Claudius Ptolemy c. 170 CE. Ptolemy, working in the great intellectual center of Alexandria, created the most significant astronomical legacy of the ancient world. Ptolemy's immense work, known by its Arabic title, the Almagest, the Great Compilation, was not a revolution, but a meticulous, serene formation. It was a synthesis of 2,000 years of patient observation and mathematical theory, primarily drawing upon the precise star data and geometric constructs pioneered by Hipparchus. The core challenge Ptolemy faced was reconciling the perfect circular motion philosophically required by Aristotle with the increasingly accurate yet stressful observations of planetary movement. The planets frequently exhibited retrograde motion, the temporary appearance of moving backward in the sky, a phenomenon that violated the aesthetically soothing concept of simple, perfect circles. Ptolemy solved this problem by perfecting the geometric complexity of epicycles and deferents. Imagine the planets moving on small circles, epicycles, which in turn moved on larger revolving circles, deferents. This intricate mechanism was a calm reinterpretation of celestial motion, a mathematical solution that ensured the philosophical integrity of the circle was preserved, even if the center of the deferent circle was slightly offset from the Earth equinoctium. The Almagest was a comprehensive guide providing the necessary mathematical tables and parameters for predicting the positions of the sun, moon, and planets with immense accuracy for its time. This achievement transformed the ancient understanding of the sky from a series of philosophical models into a robust, practical, and systematic tool for calculation. The legacy of Ptolemy's system was absolute and enduring. It provided a framework that was both scientifically useful and philosophically satisfying, as it placed the Earth, and thus humanity, at the stable central point of the cosmos. The warm breath of its influence ensured that the geocentric model, often simply called the Ptolemaic system, became the undisputed truth about the distant night across the Mediterranean, Byzantine, and Islamic worlds for over 400 years. The gentle footsteps of astronomers and navigators for centuries to come would rely on the tables and methods precisely laid out in the Almagest. The quiet stone of the Alexandrian library preserved this immense work, ensuring the continuity of astronomical knowledge through the subsequent eras of political change and upheaval. Chapter 8. Turning Points. The Islamic Golden Age and the Preservation. The serene systematic structure of Ptolemy's Almagest provided the essential legacy that ensured astronomical knowledge survived the political dissolution of the Western Roman Empire. This survival and profound advancement marked the next crucial turning point of the flourishing of astronomy during the Islamic Golden Age, 8th to 14th centuries CE. As the intellectual centers of the West experienced a period of decentralized knowledge, the centers of the Islamic world, Baghdad, Cairo, and Cordoba, became the new, magnificent sanctuaries for Greek, Roman, and earlier Babylonian learning. We view this not as a cultural conflict, but as a vast, profound, intellectual softening filter and transmission. The core philosophical task of the Islamic scholars was the methodical preservation and translation of the immense ancient archives. Imagine the House of Wisdom in Baghdad, where scholars quietly translated the Almagest and the works of Aristotle and Hipparchus into Arabic. This meticulous work ensured that the gentle footsteps of ancient reason were not lost to the ancient dust of time. This turning point was defined by a commitment to the perfection of observation. Islamic astronomers did not reject the Ptolemaic system outright, but they questioned its mathematical complexity, striving for greater elegance and accuracy. They realized that the reliance on complex epicycles and the equant offset point sometimes violated the philosophical purity of circular motion. To achieve this immense state-of-the-art, observatories were built at places like Moraga and Samarkand. These observatories were not simply buildings, but vast, quiet institutions of learning, filled with precisely engineered instruments such as massive quadrants and astrolabes. These instruments allowed for continuous, unhurried observation under the clear, distant night, compiling new, far more accurate star catalogs and planetary tables than those previously known. A key intellectual legacy of this period was the creation of the sine tangent and cotangent functions in trigonometry, expanding upon Hipparchus's work. These mathematical tools were vital for calculating celestial movements with greater precision. This was a quiet, profound evolution that streamlined and strengthened the mathematical foundation of astronomy. Figures like Al-Birun, that 11th century, and Nasr al-Din al-Tusu, 13th century, quietly and methodically introduced new geometric models such as the Tusi couple, which allowed astronomers to generate linear motion from two perfect circles. This was a subtle, elegant attempt to eliminate the philosophical stress caused by Ptolemy's non-uniform motion, the equant providing a calm reinterpretation that preserved the purity of Aristotle's eternal circles. The warm breath of this knowledge flowed across the entire Islamic world, creating a profound, shared legacy that connected mathematics, philosophy, and practical timekeeping. The development of sophisticated astronomical tables and instruments for navigation and determining the precise direction of Mecca ensured that the celestial order was seamlessly integrated into daily structured life. Chapter 9. Early Journeys. The Medieval Inheritance and the Western Quiet. The flourishing of astronomy within the organized centers of the Islamic world provided a crucial link for the next phase of early journeys, ensuring the ancient wisdom would eventually return to the decentralized intellectual landscape of the medieval West. This period was one of Western quiet, where astronomical knowledge was maintained primarily in monastic and cathedral schools. Imagine the contrast. While observatories in Baghdad and Moraga were compiling sophisticated star catalogs, the intellectual access in Western Europe was limited. The primary astronomical text available for centuries was the simple practical work of Plato's Timaeus and the elementary introduction to geometry and cosmology provided by Boethius and others. This knowledge was often fragmented and filtered through a theological lens. The core philosophical task in the West during this early journey was the spiritual integration of the Aristotelian and Ptolemaic model. The Christian thinkers viewed the serene, perfect celestial spheres as the physical manifestation of God's perfect rational design for the universe. The fixed, predictable rhythm of the heavens was seen as providing immense psychological solace, confirming the absolute order and predictability of creation. The practical application of astronomy in the West centered around the calendar of the necessity of accurately determining the dates for movable religious holidays, particularly Easter. This annual calculation required precise knowledge of the cycles of the sun and moon, leading to the formation of complex yet often decentralized methods for computation. The great intellectual turning point within this quiet period occurred around the 12th century Renaissance. This was the methodical softening filter for knowledge, where vast amounts of Greek and Islamic scholarship began to flow into Europe through two major cultural gateways. Spain, Al-Andalus, the multilingual centers in cities like Toledo, where Christian, Jewish, and Muslim scholars quietly translated immense Arabic libraries, including the Almagest and the advanced commentaries of Averroes, into Latin. Sicily, another important crossroads of cultural exchange, facilitating the transmission of Greek and Arabic texts. This influx of complete Ptolemaic and Aristotelian works profoundly accelerated Western astronomical study. The warm breath of systematic Greek logic and the precise Babylonian Islamic observations revitalized European universities, leading to the formation of scholasticism. Chapter 10 in our philosophy journey, where scholars sought to integrate the vast, rational, geocentric universe into Christian theology. The legacy of this period was not one of new discovery, but of profound preservation and transmission. The meticulous translation work carried out with gentle footsteps in scriptoriums and libraries ensured that the full intellectual architecture of the ancient cosmos was secured within the structure of European thought, ready for the next immense turning point that would challenge the very center of the earth. Chapter 10. Early Journeys, Copernicus and the Aesthetic Doubt. The comprehensive yet geocentric system of Ptolemy, preserved and refined by Islamic scholars, reigned as the quiet, undisputed truth throughout the medieval era. However, the next phase of early journeys was marked by a subtle, profound internal doubt regarding the system's aesthetic and mathematical complexity. This led to the gentle foundational work of Nicholas Copernicus, 1473–1543. Copernicus, a Polish astronomer and cleric, inherited the vast legacy of Ptolemaic geometry. He recognized the incredible mathematical accuracy of the Almagest in predicting planetary positions. But he was increasingly troubled by the system's reliance on countless epicycles deference and the complex geometric fixes required to maintain the philosophical purity of the circle while keeping the Earth at the center. Imagine Copernicus viewing the Ptolemaic model as a massive, intricate clockwork mechanism, highly accurate, yet unnecessarily complicated and inelegant. This complexity created a philosophical stress for him. He sought a simpler, more harmonious explanation for the movements of the distant night. His philosophical motivation was the quest for aesthetic harmony, a return to the serene, ancient Greek ideal that the cosmos must be arranged with the greatest possible simplicity and beauty. He questioned the fundamental origin established by Aristotle and Ptolemy. Why should the Earth, a changing and imperfect body, be the center of the perfect, eternal celestial sphere? Copernicus's solution was a gentle yet monumental calm reinterpretation of the solar system, the heliocentric model. He quietly proposed that the sun, not the Earth, was the true stationary center of the cosmos, with the Earth and all other planets revolving around it. This shift was a profound softening filter for the mathematical complexity. By moving the Earth from the center, Copernicus found that the perplexing retrograde motion of the planets, the apparent backward movement that required Ptolemy's complex epicycles, simply vanished. The retrograde motion was revealed to be a mere optical illusion caused by the faster-moving Earth overtaking the slower outer planets in their orbits. The epicycles were still needed for the Moon's motion and minor variations, but the overall system achieved a stunning new simplicity. Copernicus delayed the full publication of his work De Revolutionibus Orbium Coelestium on the revolutions of the heavenly spheres until the year of his death, demonstrating the immense cultural tension inherent in challenging the long-standing, theologically integrated, geocentric model. The legacy of Copernicus was the introduction of a new paradigm, a crucial turning point that did not immediately replace the old system. The tables were still accurate, but provided a more elegant, mathematically harmonious alternative. The warm breath of his idea began its slow circulation throughout the European intellectual community, marking the true beginning of the scientific revolution and the final structural separation of astronomical thought from philosophical and theological dogma. Chapter 11. Formation, Brahe's Golden Island and the Data. The mathematically elegant yet unproven idea of Copernicus required a new phase of rigorous formation, one built not on philosophical aesthetics, but on immense volumes of precise, observed data. This crucial task was quietly undertaken by Tycho Brahe, 1546–1601, the eccentric nobleman who transformed the art of astronomical measurement. Imagine the atmosphere in Europe following the publication of the De Revolutionibus. Astronomers were caught in a philosophical tension. The traditional Ptolemaic model was philosophically satisfying, but geometrically complex, while the Copernican model was elegant, but challenged religious and scientific origins. To resolve this, more accurate data than had ever been collected in human history was needed. Tycho Brahe dedicated his life and immense personal wealth to this pursuit. His philosophical approach was a quiet, relentless commitment to empiricism, the belief that knowledge must be derived solely from patient, systematic observation. His initial early journey was the construction of the world's most advanced pre-telescopic observatory, Uraniborg, Heavenly Castle, built on the small island of Ven near Denmark. This was not a mere building, but a massive purpose-built scientific institution serving as a peaceful sanctuary for astronomical work under the distant night. Uraniborg was filled with gigantic, precisely engineered instruments, massive quadrants, armillary spheres, and sextants. These instruments were designed to minimize measurement error, operating with a dedication to accuracy that would be unrivaled for a century. Tycho realized that the accuracy of the result depended entirely on the accuracy of the instrument and the systematic nature of the observation. Tycho's quiet legacy was his methodology. For over 20 years, he and his assistants engaged in continuous, unhurried observation, collecting daily measurements of the sun, moon, and every visible planet. This was a sustained, methodical act of formation, creating the most accurate long-term catalog of planetary positions available. This immense archive of numbers and geometry was the golden treasure that would eventually dismantle the 2,000-year reign of Aristotle and Ptolemy. Though Tycho himself remained a scientific conservative, creating his own hybrid model Tychonic system, where the Earth stayed still and the Sun orbited the Earth, while the other planets orbited the Sun, his true genius lay in his unwavering commitment to data. His methodology was a profound, softening filter for the approaching turning point. The philosophical debate was about to become an unassailable mathematical certainty. The warm breath of his influence would pass to his most brilliant assistant, Johannes Kepler, who would inherit this vast, precise archive. and through patient computation, finally unlock the true harmony and shape of the cosmos. Chapter 12. Early Journeys. Kepler and the Harmony of Ellipses. The immense accurate data collected by Tycho Brahe represented a critical moment of early journeys in astronomy, forcing a final confrontation with the 2,000-year philosophical ideal of the perfect circle. The figure who quietly took up this challenge, unlocking the true harmony of the cosmos, was Johannes Kepler, 1571–1630. Kepler inherited Tycho's vast, precise archive of planetary positions upon his master's death. A profound legacy was passed on the most accurate astronomical data ever recorded, particularly concerning the orbit of Mars. Kepler, a deeply devout thinker, obsessed with Pythagorean harmony and mathematical beauty, initially attempted to fit this data to the traditional circular and epicyclic models. Imagine Kepler's immense intellectual stress. He spent years attempting to force the meticulous measurements of Mars into a perfect circle, only to find that the data stubbornly resisted, resulting in a small yet persistent error in prediction. This tiny error, an echoing hall of discord, was the quiet catalyst that finally shattered the Aristotelian and Ptolemaic universe. Kepler's great philosophical turning point was his radical evolution to embrace a new geometric shape, the ellipse. He realized that the planets did not move in circles, but in elliptical orbits around the Sun. This discovery was articulated in his 3 laws of planetary motion, which were a profound, tranquil formation for the new cosmos. The law of ellipses: planets orbit the Sun in elliptical paths, with the Sun situated at one of the foci, not the center. The law of equal areas. A line connecting a planet to the Sun sweeps out equal areas in equal intervals of time. This quietly demonstrated that planetary motion is not uniform speed, but accelerates when close to the Sun and slows when far away. The law of harmonies. The square of a planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit. This provided the ultimate serene mathematical formula that linked the speed and distance of all planets in the solar system, revealing a deep, hidden cosmic harmony. Kepler replaced the aesthetically perfect but mathematically forced circle with the elliptical reality, finding a new, equally profound beauty in nature's own geometry. His laws were the final decisive nail in the coffin of the geocentric worldview, transforming the Copernican hypothesis from a philosophical alternative into a precise, predictive mathematical physics. The legacy of Kepler was the definitive end of the ancient era of astronomy. He completed the work begun by Thales, explaining the distant night through purely natural, observable, and mathematical laws, devoid of the need for crystalline spheres or complex epicycles. The universe was now a mechanism of quiet mathematical precision, governed by the same warm breath of law everywhere. Chapter 13. Early Journeys. Galileo, the telescope, and the break with Aristotle. The precise mathematical harmony of Kepler's elliptical orbits provided the definitive evidence against the philosophical perfection of the circle. However, the next crucial phase of early journeys required the direct visual confirmation of this new cosmos, a task accomplished by Galileo Galilei, 1564–1642, through the innovation of the telescope. Galileo's contribution was not the invention of the telescope, which was pioneered in the Netherlands, but his quiet, profound turning point in being the first to systematically point it at the distant night and publish his observations. This simple act fundamentally changed the relationship between observation and philosophical doctrine, completing the break with the Aristotelian view of the heavens. Imagine Galileo working under the cover of the quiet night, carefully grinding lenses and looking up. His observations, though seemingly minor, were immense softening filters on the ancient, rigid cosmology. The imperfect moon. Galileo observed that the moon was not a perfect, smooth, ethereal sphere, as required by Aristotelian philosophy, but possessed craters, mountains, and valleys. It was a world rough and imperfect, much like Earth. This serene visual immediately dissolved the ancient division between the flawed terrestrial realm and the flawless celestial realm. Jupiter's moons. He discovered 4 small, faint bodies orbiting Jupiter. This was a profound, quiet revelation. It proved unequivocally that not everything in the heavens orbited the Earth. The solar system had multiple centers of motion. The phases of Venus. Galileo observed that Venus exhibited phases similar to the Moon. This observation was inconsistent with the Ptolemaic model, but perfectly explained by the Copernican model, where Venus orbits the Sun inside the Earth's orbit. These observations, published quickly in his Sidereus Nuncius Stari Messenger, were a quiet, unhurried, yet devastating legacy for the geocentric worldview. They provided the warm breath of visual proof that supported the mathematical elegance of Copernicus and Kepler. Galileo's subsequent political conflict with the established authorities, which we narrate as a distant echo of institutional stress-resisting change, was the final symbolic act of the transition. His insistence on the observable empirical truth of the new cosmos over the theological authority of the old model cemented the independence of scientific observation from philosophical and religious dogma. The gentle footsteps of Galileo's telescope marked the definitive end of the 2,000-year reign of Aristotle and Ptolemy. The universe was no longer a philosophical construct of perfect circles. It was a complex physical system revealed by empirical observation. The drifting light of the telescope had forever changed humanity's place in the cosmos. Chapter 14. Turning Points. Newton, gravity, and the mechanical universe. The empirical observations of Galileo and the mathematical laws of Kepler definitively shattered the ancient Aristotelian cosmos. The next and most profound turning point in astronomical thought was the work of Sir Isaac Newton, 1643–1727, who provided the single unifying physical principle that explained why the planets followed Kepler's elliptical paths. Newton's contribution was not merely a new observation, but a vast intellectual formation that unified the terrestrial and celestial realms, a quiet achievement that completed the work begun by Galileo. He proved that the same simple, predictable laws that governed the fall of an apple on Earth also governed the distant night. The core of Newton's system was the concept of universal gravitation. This was a profound, simple softening filter for the complexity of planetary motion. Newton asserted that every particle of matter attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Imagine the sun and the planets as enormous celestial bodies engaged in a constant mutual gravitational dance. This attraction provided the necessary central force that continuously pulls the planets inward, exactly balancing the tendency of the planets to fly off into straight lines. Inertia. This balance between inertia and gravity was the perfect explanation for the elegant elliptical orbits that Kepler had described. Newton codified this understanding in his magnum opus, Philosophia Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy. This work was the ultimate legacy of the scientific revolution, providing a comprehensive mathematical description of the cosmos as a vast, predictable, mechanical universe. The warm breath of his mathematical laws governed everything from the slow tides on Earth to the orbital paths of the comets. This turning point had profound philosophical consequences. Unity of physics. It irrevocably dissolved the ancient philosophical distinction between the perfect celestial realm, Aristotle, and the flawed terrestrial realm. The universe was now a single unified domain governed by the same simple laws. Determinism. The precision of Newton's laws implied that the entire history of the universe could in principle be calculated and predicted, provided one knew the initial conditions. This introduced a new kind of quiet, absolute order into philosophical thought. The legacy of Newton was the definitive establishment of physical science as the primary method for understanding the cosmos. The gentle footsteps of his mathematics provided immense psychological solace, confirming that the universe, however vast, was fundamentally intelligible, rational, and operating with quiet, systematic precision. The age of perfect circles was finally replaced by the age of perfect, predictable physics. Chapter 15. Formation, Astronomy, and the Birth of Modern Science. The mechanical universe conceived by Newton marked the definitive turning point for astronomy, fully integrating it into the domain of physical science. The subsequent phase of formation involved the steady methodical establishment of astronomy as a rigorous professional discipline, expanding far beyond the solitary efforts of individuals like Tycho and Kepler. This formation was defined by institutionalization. The great astronomical societies, such as the Royal Society in England and the Académie Royale des Sciences in France, became the new sanctuaries for scientific inquiry. These institutions fostered collaboration, standardized methods of observation, and provided the financial and intellectual stability necessary for long-term projects. This was a calm reinterpretation of patronage, shifting support from wealthy noblemen to organized national bodies. The core philosophical shift during this time was the embrace of determinism. The success of Newton's laws led to the profound philosophical belief that the universe was a perfectly functioning giant clockwork mechanism. This view, championed by thinkers like Pierre-Simon Laplace, 1749-1827, suggested that if one knew the exact position and momentum of every particle at one moment in time, the entire future history of the cosmos could be predicted with absolute certainty. This provided immense intellectual solace, confirming that the universe, though vast, was fundamentally predictable and rational. Laplace's work synthesizing the laws of Newton with calculus allowed for the solution of complex celestial mechanics problems, leading to the formation of the nebular hypothesis. This was the first coherent mathematical model for the origin of the solar system, proposing that the sun and planets condensed slowly from a vast cloud of dust and gas nebula. This gentle metaphor of cosmic evolution replaced the older idea of a single, instantaneous creation. The legacy of this period was the transformation of the astronomer from a philosophical observer to a precise, practical physicist and mathematician. The focus shifted from describing the orbits Kepler to explaining the subtle deviations and perturbations caused by the complex gravitational interactions between multiple planets. This meticulous, unhurried calculation provided the final quiet confirmation of Newton's theory. The gentle footsteps of progress were now defined by improved instrumentation. New telescopes with larger, more precise lenses and mirrors were developed, allowing astronomers to collect more drifting light and observe objects fainter and further away than ever before. This continuous improvement in technology cemented astronomy's position at the forefront of scientific exploration, setting the stage for the immense quiet discoveries of the subsequent centuries. Chapter 16. Turning Points. The discovery of new worlds. The serene deterministic cosmos established by Newton provided the stable framework for the next major turning points, a phase of quiet, systematic exploration that led to the discovery of entirely new worlds within our own solar system. This era marked a profound expansion of the astronomical formation, pushing the boundaries beyond the planets known since antiquity. The core of this period was the transition from philosophical speculation to methodical survey. The vast, precise measurements accumulated since Tycho Brahe and unified by Newton's mechanics allowed astronomers to predict subtle gravitational influences, with great accuracy guiding their telescopes to new discoveries. The first quiet triumph was the discovery of Uranus by William Herschel in 1781. Herschel, a gifted musician turned astronomer, was systematically observing the distant night when he noticed a faint object that moved too slowly to be a comet. His observation confirmed the existence of a planet orbiting far beyond Saturn, the outermost planet known since the time of the pre-Socratics. This discovery was a monumental softening filter on the ancient confined view of the solar system, proving that the solar system was far larger and more expansive than previously imagined. The second major turning point was a triumph of pure mathematics, the discovery of Neptune. After meticulous observations of Uranus revealed minute persistent deviations in its orbit, astronomers realized that these tiny stress points were not errors, but were caused by the gravitational tug of an unseen, massive body. Working independently, Urbain Le Verrier in France and John Couch-Adams in Britain performed the intense quiet calculations based entirely on Newtonian mechanics to predict the precise location of this missing planet. Neptune was subsequently found exactly where predicted in 1846. This discovery was a colossal legacy for scientific thought. It confirmed beyond any doubt the absolute predictable power of Newton's gravitational laws. The entire universe, it seemed, was a perfect clockwork mechanism that could be solved with mathematics even before it was observed with the telescope. This achievement instilled immense intellectual solace and confidence in the methodology of physics. The continuous, methodical survey of the sky also led to the discovery of the asteroid belt between Mars and Jupiter. These small, quiet stone remnants, beginning with Ceres in 1801, provided a gentle metaphor for the immense dynamic processes that shaped the early solar system. The warm breath of this era was the belief that all celestial phenomena could be explained through universal, predictable laws. The gentle footsteps of astronomers were now guided by the unwavering hand of mathematics, continuously charting the boundaries of our cosmic neighborhood. Chapter 17. Early Journeys. The rise of stellar astronomy. The immense success of Newtonian mechanics in charting our solar system created the stable foundation for the next phase of early journeys, which turned the focus outward away from the planets and toward the distant stars. This was the quiet birth of stellar astronomy, the study of the stars as individual physical suns, not just fixed points of light. This profound intellectual shift was a direct continuation of the legacy of Tycho Brahe and Hipparchus, driven by two key observations. Stellar parallax. The ancient Greeks had recognized that if the Earth truly orbited the Sun as Copernicus proposed, then the apparent position of nearby stars should subtly shift throughout the year. Stellar parallax. They failed to observe this shift, leading them to conclude the Earth was stationary. However, with improved instrumentation and precise data collected since the time of Tycho, astronomers quietly embarked on the long, difficult quest to finally measure this tiny shift. This methodical work, requiring immense patience and skill, was a profound, gentle metaphor for the commitment to empirical proof. The eventual successful measurement of stellar parallax in the 1830s provided the final, unassailable physical proof of the Earth's orbital motion. Stellar motion. William Herschel, after his discovery of Uranus, dedicated his life to surveying the entire distant night with his powerful telescopes. His methodical observations revealed that the stars were not perfectly fixed, as had been assumed since antiquity, but were subtly moving over time, a phenomenon known as proper motion. Furthermore, by observing double stars' binary pairs, he confirmed that these distant celestial bodies were orbiting each other, proving that the same Newtonian laws of gravity that governed our solar system also governed the entire universe. Herschel's immense legacy was the realization that the Milky Way, the faint cloudy band visible in the quiet night, was not a unique cosmic entity, but an immense vast collection of stars, of which our sun was only one. He attempted to map the size and shape of our galaxy using the gentle footsteps of his telescope to survey the celestial structure. This era represented a quiet, yet fundamental softening filter on humanity's place in the cosmos. The sun was no longer the unique, powerful center of the universe, but one star among millions, a profound intellectual evolution that was nonetheless accepted with serene scientific contemplation. The warm breath of inquiry began to focus on the nature of light itself. The invention of the spectroscope allowed astronomers to move beyond position and motion and begin analyzing the chemical composition of the stars, transforming astronomy into astrophysics, the study of stars as physical evolving objects. Chapter 18. Turning Points. The rise of astrophysics and cosmic chemistry. The rise of stellar astronomy, which established that the stars were distant suns governed by Newtonian physics, paved the way for the next profound turning point, the birth of astrophysics. This monumental shift transformed astronomy from a science of position and motion into a physical science of chemistry, temperature, and evolution. The core of this revolution was the invention of the spectroscope in the mid-19th century. This instrument, which we view as a quiet, precise mechanism for deciphering the drifting light, allowed scientists to break down the light emanating from distant celestial bodies into its constituent wavelengths, a spectrum. This was a fundamental methodological evolution. Imagine the scientist gazing at the spectrum and the appearance of specific dark or bright lines within the rainbow of light provided an unassailable legacy. They revealed the precise chemical composition of the stars. This application of terrestrial physics to the distant night proved that the same elements found on Earth, hydrogen, carbon, iron, etc., existed throughout the cosmos. This was a profound, softening filter for the philosophical gap between the terrestrial and the celestial realms, definitively confirming their unity. The work of physicists like Gustav Kirchhoff and Robert Bunsen established the laws of spectroscopy, ensuring that the warm breath of inquiry could now determine the temperature and pressure of stars simply by analyzing their light. This technological leap immediately led to a new series of quiet, immense discoveries. Stellar classification astronomers, particularly Edward Pickering and the Harvard computers, a team of meticulous women classifiers, including Annie Jump Cannon and Henrietta Swan Leavitt, undertook the immense, unhurried task of classifying hundreds of thousands of stellar spectra. This methodical process led to the formation of the modern stellar classification system, categorizing stars by their chemical composition and temperature, OBAFKM. This revealed the systematic structural order in the vast stellar population. Cosmic distance, Henrietta Swan Leavitt. Early 20th century discovered the period luminosity relationship for Cepheid variable stars. This finding a predictable correlation between the pulsation period of these stars and their true intrinsic brightness was a quiet yet immense turning point. It provided the first reliable standard candle for measuring the vast, previously unmeasurable distances to galaxies far beyond the Milky Way. This achievement was a crucial, gentle metaphor for the power of meticulous observation, transforming the universe from a single galaxy into a multi-galactic expanse. The legacy of astrophysics was the realization that stars were not eternal fixtures, but objects with a life cycle. A quiet, predictable evolution from birth in nebulas to eventual death as white dwarfs, neutron stars, or black holes. The gentle footsteps of chemical analysis had successfully revealed the dynamic, evolving nature of the entire cosmos. Chapter 19. Early Journeys. The expansion to cosmic distances. The meticulous measurements of stellar composition and motion achieved by astrophysics provided the necessary stability for the next phase of early journeys, the quiet, methodical expansion of our cosmic view far beyond the confines of our own galaxy. This was the quest to establish the true scale of the universe. The most challenging obstacle inherited from the ancient past was the sheer immensity of cosmic distance. Measuring the distance to the stars, even within our own Milky Way, required immense precision. But measuring distances between galaxies seemed impossible, pushing the limits of human comprehension. The key to unlocking these vast distances was the legacy of Henrietta Swan Leavitt and her discovery of the period luminosity relationship for Cepheid variable stars. This finding, a quiet, predictable correlation between a star's pulsation rhythm and its true intrinsic brightness, provided astronomers with the first reliable standard candle. Imagine this: as a universal lantern glow of known intensity, allowing us to gauge distance simply by measuring how dim it appeared. The systematic application of this method was the Great Early Journey, led by Edwin Hubble in the 1920s. Using the powerful telescopes on Mount Wilson, Hubble quietly embarked on the profound task of observing faint, fuzzy nebulae that were scattered throughout the distant night. Hubble's observations were a monumental softening filter for the scale of the universe. By locating individual Cepheid variable stars within these nebulae and applying Leavitt's law, he was able to calculate their immense distance. His conclusion was simple yet devastating. To the established view that these nebulae were not small clouds of gas within our Milky Way. They were colossal independent galaxies, vast island universes, each containing billions of stars situated millions of light years away. This discovery was a definitive turning point, a quiet, absolute end to the centuries-long assumption that the Milky Way represented the entirety of the cosmos. The universe suddenly expanded by orders of magnitude, transforming the astronomical formation from a single galaxy into a universe of uncounted galaxies. Furthermore, Hubble made another profound observation. During this early journey, nearly all galaxies are moving away from us, and the further away a galaxy is, the faster it is receding. Hubble's law. This was a fundamental legacy. It demonstrated that the entire universe is not static, as had been assumed since the time of Aristotle and Newton, but is expanding. The warm breath of this discovery implied a startling origin. If the universe is expanding now, it must have been smaller in the past. This quiet realization laid the intellectual groundwork for the Big Bang theory, the modern scientific model for the birth of the cosmos. The universe was no longer an eternal clockwork mechanism, but a dynamic, evolving entity with a definite beginning. The gentle footsteps of these measurements had opened up the immense, accelerating realm of cosmology, ensuring that the quest for the origin of the universe would become the final great task of modern astronomy. Chapter 20. Legacy, the Cosmic Lullaby, and the Final Question. We arrive at the final chapter of our long, slow ascent into the cosmos. The universe has been transformed from the perfect small geocentric spheres of Aristotle and Ptolemy into a vast expanding multi-galactic expanse revealed by Hubble and astrophysics. This final phase focuses on the enduring legacy of this journey and the ultimate quiet question it leaves behind. The greatest legacy of astronomy is the complete softening filter it provides for the human perspective. The initial fear and stress of the unpredictable cosmos, which compelled the Babylonians to record and the Greeks to theorize, has been replaced by the profound solace of scientific understanding. The discovery of universal physical laws from Newton's gravity to the speed of light has confirmed that the universe is fundamentally intelligible, rational, and predictable. The core philosophical shift that endures is the acknowledgement of cosmic time. The warm breath of human history spanning a few thousand years is now measured against the billions of years of cosmic evolution, the long, unhurried journey of stellar birth, galactic drift, and universal expansion. This immense timescale offers a serene perspective, reducing the immediate chaos of daily life to a mere gentle metaphor in the context of eternity. The legacy of the celestial myths also persists. While scientific inquiry replaced the need for gods to push the planets, the ancient desire to find meaning and narrative in the distant night remains. The constellations, once literal guides for navigation and agriculture, are now the collective shared legacy of our ancestors, providing a universal, tranquil visual language. The quiet stone of ancient observatories like Stonehenge and the precise calculations of the Babylonian scribes are now understood as part of a single, continuous human search for order. The ultimate question left by this journey returns us to the origin of philosophy itself. Why is there order rather than chaos? The Big Bang theory describes the beginning, and physics describes the rules, but the serene existence of these precise, elegant, and predictable laws remains the final beautiful mystery. The universe, having revealed its mechanics, now presents its metaphysics. The story of astronomy is the longest, most patient study in human history. It is a cosmic lullaby affirming that though we are small, the human mind is capable of comprehending the immense silent harmony of the drifting light that surrounds us. The universe continues to unfold, governed by the same warm breath of law, waiting patiently for the next quiet realization. The long night's watch is over. In this quiet journey tonight, we drifted through the gentle echoes of the history of ancient astronomy and celestial myths. We moved from the first gaze under the origin of night and the systematic formation of the Babylonian tables, through the turning points of Ptolemy's spheres and Newton's gravity to the vast, expanding legacy of modern astrophysics. We followed the rhythm of the stars from their earliest beginnings to the soft traces they leave behind in the foundations of our knowledge. The story of astronomy reminds us that the greatest leaps in understanding come not from speed or conflict, but from patience and quiet, meticulous observation. It teaches us that the universe is governed by profound, elegant laws, and that our greatest solace lies in recognizing our connection to the silent, predictable harmony of the cosmos. If this peaceful journey brought you ease, you may leave a soft like, or whisper in the comments where you'd like to drift next. And now, let the night grow still. Let your breath slow. May sleep come softly and carry you into peaceful rest. Good night.